All right, it's 40 after, so let's go ahead and get started. The reading this week is chapters 6 and 7, and the topics are going to be work and energy and power. So we're getting into energy now. Very super important topic in physics, actually in all of human society. Energy is very important. We're going to also in chapter 7, and what we'll do maybe at the end of the lecture today, we'll get into a little bit of it. But next lecture we're going to talk about a lot. The conservation of energy is really crucial. It's such a basic concept. I think most physicists think of conservation of energy as being, in some sense, more fundamental than Newton's laws in a way. It's almost like it's a deeper idea, and these things are all related though. As we'll see, there are direct ways to use energy to think about the change of motion of objects directly with energy. All right, so we'll get there. But first, let's define what we mean by work. So this is, when I was a student, I thought this was a swindle. I thought it was a scam, or sort of a stupid definition. In physics, at first, eventually I learned that it was a good idea. But the idea was that work wasn't defined by how much exertion I put into something. Work was defined by the amount of force times how far the thing that's being pushed moves. That's what work is. And I thought that was silly, because if I'm holding a weight, suppose I'm supporting a weight, I'm holding a big heavy suitcase, I'm standing at the bus stop, I'm holding that suitcase, and I'm sweating, and I'm working hard to hold that suitcase. I feel like that should count as work, but it does not. The physics definition of work, and it depends on what's being fixed. So there's a bunch of different ways to write it, but let's write the most general way first, and then I'll write a bunch of different ways. It's from position 1, so R1, R is my radius vector from where my origin is, so my position 1 to position 2, some integral, right, of the force, which is a vector, and a dot product of that vector with my little infinitesimal change in the position of the object. And I go all the way from my initial to my final point. And that's the definition of work. So that's its most general form, right? We've written this as a three-dimensional vector. This is a dot product, or an inner product. Who has not seen a dot product before? People haven't seen it, but most of you have seen it. So those of you who haven't seen it, there's a couple different ways to think about dot product. An inner product. The way a mathematician might say that the dot product is a way of mapping a pair of vectors into a number. It's a way of mapping two vectors into a number. You start off with two vectors, you take your dot product, and you get a number out, right? So how do I do that? There's a couple different ways to write it. One is to write it in terms of components. So here, I'll just write a couple general statements about dot product. So if you have two vectors, A and B, you take your dot product. What is that? Well, that is just the sum of the products of their components. So I'd say, it's A sub x times B sub x plus A sub y times B sub y. And if we're three dimensions, that's for a two-dimensional vector. For three dimensions, I would also add A sub z times B sub z. So if you have two vectors, A and B, you take your dot product just by element-wise multiplication and sum them up, right? So that's what we mean by the dot product. It turns out it also has another geometrical interpretation. If you have a dot product between vectors A and B, so here's vector A and vector B drawn pictorially on here, right? And there's some angle between them, theta. I'm saying, all right, what's the dot product in terms of theta? So who knows what's the dot product in terms of theta? What trigonometric function of theta do we need for the dot product? Cosine, that's right. The thing is, dot products are big when vectors are co-aligned. And they go to 0 when the two vectors are orthogonal to each other. And they go to the largest negative value they can take when they're pointing in the opposite direction of each other. So the thing that does that is cosine, right? So cosine goes like this, starts off positive 1, its biggest value. Here's cosine of theta as a function of theta, right? And then when you get to 90 degrees, it's equal to 0, right? So here's 90 degrees, or it's like pi over 2 radians, right? And then so on. That's when you're 180 degrees, that's pi radians. So that's when you're pointing in the opposite direction of the two vectors. So when we write this then, it's like this. It's like, it's the length of A times the length of B. And here these don't have vector signs over the top, but by this I mean the positive length of A, the positive length of B. And I multiply by cosine of the angle between them. So that's all I mean by a dot product, or the inner product. It maps these two vectors onto numbers, right? Onto a single number. So this is a single number. You sum these up. This isn't like a pair of numbers here. Same thing here. Number times a number times a number times a number. Okay, great. And it can be positive or negative, as we just discussed, right? It's just depending on what the angle between the two is. Great. So if we go back to our definition up there, if we have a force that's constant, and we say, okay, well, let's choose our x-axis to point in the direction of the constant force, right? So if we just have some constant force, right, that's pointing in the x direction, what we can do is we can make a simpler expression and say, the work then is just equal to the x component of the force times the change in the x position of the object, right? And also, so constant. I mean constant. Yeah, that's right. It's constant. And I'm using it in two different ways. I'm using that for the entire path I take with the particle that's moving from R1 to R2. The force is always pointing in the same direction, always has the same magnitude, and I've chosen also to point it in the x direction, right? So I use both those factors. So I don't have to worry about the x component of this thing, right? Well, the integral of dx from x equals x1 to x2, so all I mean by delta x, right, is the final x value minus the initial x value. That's all I need, right? And I've got my sign right here. Delta x is positive if x got bigger. If x initial is smaller, it's a smaller number than x final, then this is a positive delta x, so I get positive. So the work is positive if the object you're pushing on, right, moves in the direction you're pushing it, then you did positive work on the object. So just like with forces, we have to keep track of, is it the force by this thing or is it the force on that thing, right? It's really important to keep that straight. Same thing true for work. So in particular, when I say that the work here, I'm going to ask, I'm in subscript. When I say the work equals the integral of dr, I mean the work on some object is the force on that object, right? And if I want to know what the work by it is, I want to know what the force by it is, right? In other words, if I'm exerting a force on this chalk right now, which I am, let's say I do this, let's say I'm exerting some force on the chalk, I move it up like that. So first of all, am I doing positive or negative work on the chalk from now to now? Positive, because what direction is the force of my hand on the chalk? It's up. And which way does it move? Up, right? So how about the chalk on me? Is the chalk exerting a force on me? Yes. Which way is that force point? Down. So if I do this, is it positive or negative work the chalk is doing on me? Negative work. Now, how many forces are acting on this chalk during this, while this happens? 2. That's right. As long as there's no wind resistance or anything else going on, there's no magnets, and there's only 2 forces, right? There's the force of my hand on the chalk, and there's the gravitational force on the chalk. Now, while this guy's moving, if he's moving at a constant velocity, then what's the acceleration on the chalk? 0. So if we went to Newton's second law to calculate what the net force must be, right? What's the net force on the chalk during this time? 0. So if we ask for the net work that's performed on the chalk, what's that going to be? Yeah, the net work on the chalk is just this formula, right? Where I define x as my axis, vertical axis. It doesn't matter if I define it up or down, by the way, I'll get the same sign, because both these guys will change signs if I change the direction, right? But we'll talk about that in a minute. So as I go up like that, the net work is 0 because the net force is 0. So I have a net here and net here. I say, well that's 0, so there's no net work performed on the chalk, which makes sense. Another way to say it is, well, I'm doing positive work on the chalk, but gravity's doing negative work on the chalk by the same amount. So if we add those together, plus the work I did, minus the work, minus the absolute value of the work that gravity did, and you wind up with 0. So that's another way to think about it. So the net work on an object is the sum of the amount of work done by all the forces, or you can just go ahead and take the net force acting on the object and plug it into this formula, and I'll tell you what the net work is. So there's a lot of important concepts there. One is work on something as opposed to by something. And that's just a matter of keeping straight. If you want work on, you better use force on, right? The next thing is whether it's positive or negative in terms of whether this is lined up with that or not, right? Another thing that's important as we go, in a couple boards, if we do a little more work, it'll turn out to be important that in this case the net work was 0, and so that by the work energy theorem, it'll tell something about the final speed of the speed of the guy after he's moved for a certain distance after it's been affected by some work, by some force. All right, so that product's all right. Make sure we cover all the sort of basic. Right. Well, let me ask you this then. So right now I'm exerting an upward force on the chalk, and let's say I walk this way. So now how much work am I doing on the chalk? I'm doing 0, right? Because the vertical displacement of the chalk is not changing, only it's horizontal, and the force I'm exerting on the chalk is vertical. So when I take that dot product, I'm going to get 0. So I'm doing no work on the chalk, even though there is some displacement. What else should I ask you? Well, what if I take some angle? Well, we've already worked this out. If I do some work on the chalk, and let's say I move it at an angle, and I ask the question, how much work is, let's ask how much work is gravity doing on the chalk? Now, if I start right here, and I move this way at some angle, theta, which is the horizontal. So first of all, is gravity doing any work on the chalk? Is it positive or negative? It's negative, for the same reason it was when I went straight up. But how much is it going to be? Well, if I know what the angle is, right, that's, okay, well, here's theta, and here's the trajectory, here's my initial position, R1's right here, and then here's my final position up here, R2, right? And I've got some angle like that, and I know the whole time gravity's acting straight down with mg on the chalk, right? So it's a constant force situation. I can use that equation and then stick it, I know what the direction of the force is straight down, but I have to be careful because let's see, can I use this? I can use this formula, but I have to be sure to make sure that my x-axis is aligned with the force. The force is pointing straight down. So okay, let's define this to be our x-axis. So that's lined up with our force. It's pointing in the opposite direction, so we're going to get a minus sign. So in this case, I'd say, okay, work by gravity on chalk, right? To be pedantic, right? So, all right, that's just going to be force due to gravity. And we know that that's and we want the x component to that, right? Which actually is the whole thing, right? And then we say let's multiply that by how far the thing moved, but only in the x direction, right? We don't put down the displacement in terms of r's. We say, oh, it's only the x direction that matters. In other words, what I've done is I've taken the dot product. I'm just asking for the vertical displacement. So for this definition of theta, is that going to be cosine theta or sine of theta? It's going to be sine of theta. So just be careful with your definition. The cosine of theta here, that happens because we're talking about the angle between the two forces in the dot product. Let's see. In this case, I've got, I see, yes, because I define theta to be from the horizontal, not from the direction of the force. So if I'm going to use the same definition of theta up here, just to be clear, maybe I'll use a different symbol so it's not, I'll call it alpha. All right. And then I can say, all right, what is this going to be? It's going to be whatever that force is, it's mg, right? Oh, it's negative because the x component of it has a negative value, right? Now I multiply by delta x, that's positive because it went from here to there. So the x increased, but not by the full L, not by the full distance I translated it from here to here. So if this distance is a meter along L, it'll be less than L. It's going to be L times, as you all correctly said, L times sine theta. Excuse me, sine alpha, because I gave you a different name, just to avoid confusion with this different definition for theta up here. Sorry? It's along the vertical axis, and I called it x because I felt like it, I called it X. But I could have called it y. If I did that, then I would have had a sub y here and a y right there. So I wind up with negative, it's negative work, as you correctly stated, it's negative mg L. But what is this thing? Well, all this is just the height, right? And in fact, if what we did, and the h, I just need a positive number, it's just a positive height. It's just this height right here, right? So in general, if you have a force like gravity, so gravity is a particularly simple force in the sense that it's always the same value for a given object. The force on me is different than the force on this chalk because I'm more massive than the chalk. But for a given object that's not changing its mass, like this chalk, the force is always pointing the same direction, and it always has the same magnitude. That means that we can define a type of potential energy for gravity. And it also means that there's a really ezy way for us to calculate the amount of work that was done by gravity on this object that doesn't involve having to know all the details about the motion that the object took in order to get from point A to point B. All you have to know is the change in the height of those two positions. So like if you go through a calculation like this for every little segment of some winding curve that maybe I took, so suppose I want to go up the top of a mountain, right? And I'm a pointy mountain. So when I go up the top of this mountain, well, I could just do it straight up, right? Or whatever. I could go to the center of the mountain, take a tunnel to the center of the mountain, go straight up the center of the mountain, top to a volcano. That's one path I might take. If I did that, it's pretty straightforward. You say, oh, it's just the height of the mountain, right? Times the force of gravity on me, that's mg, so it's mgh. That's how much work, let's see, it'd be the work that gravity did on me, right, on me, would be negative, my mass times g, centimeters per second squared, times the height of the mountain. Just because all I did, I took that height and said, okay, that's h, and I just plugged it into this formula, right? And said, oh yeah, and it's negative because the force of gravity is pointing down, but delta x, or delta r, if you want to do it more generally, is going up, right? So they're in opposite directions. But what if I took a winding path, right? What if I started off, I took a bunch of switchbacks, right? And I went all the way up the mountain like that, along some route in my car, right? And I asked, well, what's the work that gravity did on me in that case? Well, it's going to be the same, right? Because if we go through this calculation for every little switchback, right? For this, we get this height right here, here's some big L and multiply by whatever sine of this alpha, and then we do it here and we do it here. It's just going to be adding up these heights, and it's the same answer. So it's path independent. This is a really powerful idea. This is what's going to make it so much easier to solve a lot of physics problems for us. That when we start thinking about work and energy, it just gets a lot easier than having to use F equals ma at every little spot along the way and keep track of what the velocity was and every stage along the way. Because and not only that, but we didn't talk about my velocity here, right? We didn't talk about how fast I was going. We didn't talk about how long it took. All we had to keep track of was what was the difference in my height from the beginning of the day to the end of the day when I got to my destination. And then somebody says, oh, how much work did gravity do against you? Which is what my hiking friends will ask. And I'll say, oh, it's negative mgh. And if I just know, and I check my fancy watch, it tells me the elevation. That's not true, but if I had such a thing, then I would say, oh, the change in elevation was this much, multiplied by mg, put a minus sign in front because gravity did negative work on me, right? And I'm done. Doesn't matter what path I took. Really powerful idea. Great. And in fact, it doesn't even be like this. This isn't an easy example in the sense that this part right here is just like an example of a straight line. Even if this were a winding path. In fact, even if the path involved me going back down for a little while and sort of looping around and doing some crazy path, it doesn't matter. And you might say, well, wait a minute, what if you go back down again? Doesn't that change the answer? Well, whatever work I did to get up to here, or whatever work gravity did on me, let's say, to this point, you say, well, maybe I got some positive work in gravity going back down. Yeah, but you gained it back when you did this extra piece of loop over here. So you get up to this point, you go back down here, and then you go back up here again. Well, this negative part, positive work by gravity here is offset by the negative work by gravity here, and they cancel out, and it's as if you never went back, right? You just kept going up. So it just works out really nicely. And in order to handle the smooth curve, I would do the same trick I did here, just that this would be a little DL, a little differential L, and differential H with different, anyway. All right, but I'll spare you that. So there you have it. That's a great thing. So I mentioned a minute ago about potential energy. What do I mean by potential energy? Whenever you've got a force that depends only on position, or I should say it depends at most on position. So gravity is independent of position. It's always the same. It's always, for a given object, the force of gravity is always m times g pointing straight down, right? Doesn't matter where you are, doesn't matter how fast you're moving, and it doesn't matter which direction you're moving, right? The force is the same. So for forces like gravity that only depend, and I'll say at most, because they don't have to depend on position, it's just that it's okay if they do, at most, on position, right? On where you are. That's all they care about. You can define a potential energy. So I'll write PE, potential energy. The book sometimes will use U or I think even P sometimes. I tend to write it PE, potential energy. It's easier for me to remember. Potential energy. And what is potential energy? It's just minus the work. I should say too that I'm defining here a change, delta PE, a change in the potential energy. I'll talk about the 0 point of this in a minute. But from some position to some other position, right? From R1 to R2 and it's just going to be the work. It's just going to be the force that's on the object in question, whose energy we're talking about, right? And it's a vector, dotted in general, dotted with a dr. Right? So this is just the definition of work we had, except I got a minus sign in front. And why a minus sign? So here's the idea. If I raise this chalk up, then gravity did negative work on the chalk, right? Because gravity, as you all stated, force of gravity points down, I displaced it upward, you take the dot product, you get a -1 for the cosine theta term, and then you get minus mgh, right? Well, in terms of potential energy, what does potential energy mean? Potential energy is stored up energy that potentially could be converted to something else like kinetic energy, which we'll talk about in a minute. Energy, some other kind of energy of motion in that case. So if you raise a block up, or whatever, a piece of chalk, raise this piece of chalk up, it has increased its potential energy as a result of this. If I let go of it, and then wait to see what happens when it gets back down here, it's going to be moving faster than 0. So I started, it's not moving at all, right? 0 velocity. I raise it up by some height, and now if I let go and let gravity act on it, well, now gravity's going to impart positive work on it. It's going to do positive work on the chalk and speed it up. So what this definition does is, because of this minus sign here, and the fact that this is the force on the object from whatever it is, if it's PE of gravity, then you put a G here and a G here. There's other kinds of things that can give potential energy, like springs, right? But for gravity, in that case, raising it up means that gravity did negative work, but that means the object acquired positive potential energy of gravity. And that means that if you then release it and let gravity do work on it, it'll be positive work gravity does this time, and that'll result in this thing increasing its kinetic energy, or energy in some other form. Potential energy is the energy that can be potentially turned into any other kind of energy. You might say, well, what kind of energy is there? Well, it'll turn out that there's some kinds of energy that you can't convert into any kind of energy you want. But gravity provides potential energy. It provides a way of storing energy up that can be converted into whatever you want. Can do useful work, right? So good. We can define potential energy for gravity. And in fact, we can write a simple formula, like this is potential energy for any type of a force that has this property that only depends on position at most. So it's also true for springs, right? Springs have potential energy. And there's other kinds of potential energy too, but those are the two we're going to see most of the time in this class. So in general, we can write down a formula for the change in the potential energy of gravity, right, of some object, and that is just going to be mg times the change in the height, where a positive change in the height results in a positive change in potential energy. So this sort of begs the question, I've written deltas on both sides of this equation, but what is the absolute, what is the value of something's potential energy at any moment in time? Well, it turns out there's no, in some problems, like for springs, for example, as we'll do in a few minutes, it'll turn out that there is a well-defined place we're going to call zero potential energy. There's a sort of natural place to put it. But for gravity, there's no natural place to put it. So it's just like your choice of an x-axis. You can choose to put the 0 point where you want. So when you solve a problem, you're going to use potential energy of gravity. You're going to choose some place as the 0 point for your potential energy. The same way you do for your x-axis and your y-axis. You choose an origin. That seems kind of weird because energy is, it's a physical concept, not just a matter of, like labeling where you are. But it's true that, there's no preferred location for 0. There's no height equals 0. In fact, if you're on different parts of, like if right now we're underground compared to the ground level up there, but if I want to use potential energy equal to 0 on the ground in the room, I'll do that, right? To make my problem simple. So I have 0 show up in my equations and simplify things for me. That's fine. Now that's not true for kinetic energy. We're not defining kinetic energy right now while we're at it. We'll get to this. We'll talk more about the consequences of this in a little bit. So there's all different forms of energy, right? Energy can be stored in the battery in your cell phone, or it can be, sunlight from the sun and everything. We're going to all these, as the course goes on, we'll cover all these things at some level. There's a special form of energy which is just, it has to do with the motion of the object, right? So who has not heard of kinetic energy? Only one person. All right. For you, it's important to know. And so it's going to be reminded, though. It's going to be reminded. Kinetic energy is 1/2 mv squared. And that might puzzle some of you, or puzzle you. Suppose you've seen it, so you're not puzzled at all. Let's just accept this 1/2. Oh yeah, that's the definition. That's kind of weird, there's a half here. Why should there be a half in this definition? It'll turn out that if you take a b and you learn about relativity, you'll find out where that half comes from. But for today, I'll just mention that, don't forget to put the half in. This is m. Turns out it's the same old m you use for everything else. It's mass. So, and that turns out to be a deep concept which gets into general relativity. Like why should it be that mass, as we define it for momentum and for F equals ma and all this stuff, why should that be the same as the m here? Anyway, deep ideas. But for us, yes. All you have to know is that for any given object that's got some mass, whatever it is, and you stick it in for m and then the velocity v. Notice that this is v squared. That's important for a few reasons. One is that it tells you that it's always positive. Doesn't matter which way the velocity is pointing, right? So if I take this chalk and I throw it, that would never do. If I were to do that, and it's flying that way at some fast speed, right, some velocity, if I know what kinetic energy, I'd say, oh, the chalk has kinetic energy 1/2 times the mass of the subject times v squared. Well, whichever way it's going, it's the same kinetic energy. Kinetic energy is a scalar, it's a number, and kinetic energy is always going to be positive or 0. It can be 0, but it's non-negative. Unlike potential energy. So potential energy, depending on where I choose my 0 point, can be negative. You can certainly have a problem where the gravitational potential energy goes negative, right? But you should never have the kinetic energy go negative. There's no velocity you can plug in here or mass. Mass is always positive, right? There's no mass or velocity you can plug in to get a negative number for kinetic energy. So remember, kinetic energy is always positive, and it sort of makes sense, right? Like if I have a piece of chalk like this or whatever.